Welcome to our lecture about minimum spanning trees. We're going to begin with a very simple example. Let's assume that the telephone company is trying to figure out its network and particularly how to lay telephone wire in order to connect its possible subscribers. The typical setup is that there is a central office that somehow has all of the routers, hubs, and necessary networking equipment in order to set up the network and allow the subscribers to use the services. The naive approach would be to lay cable from the central office to each house. Of course, this is unrealistic and it's very expensive. A better approach would be to attempt to minimize the total length of wire connecting the customers. The way to do this is by trying to figure out, in a sort of a network and graph theory basis, how this would be achieved. Here comes the spanning trees that we talked already a little bit in the class, and we want to figure out the minimum spanning tree. And minimum spanning trees are, for all intents and purposes, subgraphs. We assume that the full graph is the entire network, and we are trying to find the one that is a subgraph, and it will allow us to optimize how we connect it. For all intents and purposes, it is a tree, and it needs to make sure that it's not only a tree, but it's also an acyclic tree. This is important. We cannot have cycles. It covers all the vertices, and in order to cover all the vertices, it should have v-1 edges. Now, we associate some kind of a cost whenever we set up this minimum spanning tree. Now, the vertices that they are connected, or better yet, the edges that they're connected, they have some weight. The weight in our case could be the length of the connection. In other cases, it could be the cost in order to be able to transmit the information. The point that we're trying to make sure that we have is that we're trying to construct a subgraph that is acyclic. It covers all the vertices, in our cases, all of the subscribers, all of the customers, and the total associated weight is the minimum that we can obtain from the graph. So the question is a more general one. Given a graph like the one that we see here on this side, is it possible to identify in some kind of an algorithmic way the minimum spanning tree by preserving all of the necessary properties that we have mentioned below: acyclic, minimum weight, and all the vertices connected? The algorithm to do that is based on Prim. Prim's algorithm was developed some time ago in the late 60s, and the idea behind it was that the way to determine how the algorithm works is based on the vertices. And we make this distinction because there is another algorithm that identifies minimum spanning trees. It's called Kruskal's algorithm, and that is based on edge computations. But here, we start from a vertex R to be the root, and it is perfectly fine to pick any one of them, but for the sake of argument and for the sake of the example, I will just pick A. Then what we do is we set the parent and to null, because we know that there is a root, therefore there is no parent. And then we assume that A has all the connections possible from the undirected graph. So to provide an example, A is connected to 9, it's connected by 9 to B, to D, and then to C. This means that if you look at here, we set A, B, if you see A, B, C, and D, sort of we initialize them and we set them to infinity. Well, we definitely know that the graph edges are not infinite. but they have specific weights. From A to B is 9, from A to D is 2, and from A to C is 5. So as we're looking at this graph now, we realize that we have the notion, or sort of the idea, of the horizon of A across the network. This is what the first subgraph that we have would be. So while we know that the root is not empty, what we do is we select the next vertex and we start adding things. And what we do is, remember before in the slide we had infinity. We now don't treat infinity anymore. We update the weight of each vertex W adjacent to U, where U in our case is the root node, or A. As long as it's not on the tree. And what we do is we are trying to compare the two, and this part is this section of the algorithm that you see here, the if statement, in order to be able to check what the weights would be. So if the weight is lower than the next one, then we will select it. And then what we do is we update our priority queue, which is our storage area, with the new distance for W. And as we do this, we build more and more parts of the minimum spanning trees in order to figure out which ones would be the minimal. Now, from computational complexities perspective, the running time, if we don't use heaps, because heaps have a very special setting as a data structure, the initialization of the priority queue is big O of the number of vertices. So this is pretty obvious because we only have what we need to update. When we go into the update loop, which is probably one of the most expensive parts, is that we choose the vertex with a minimum cost edge, and that the cost is also trivial. But the problem is that every single time that we're doing this, we are running it within a loop. And by virtue of running it within a loop, we are running it V times here, the number of vertices, and then another time here. This caused the loops to end up to square. And this is why the overall cost ends up being the number of edges, big O of the number of edges plus the number of vertices square. The square comes from the nesting of the two update loops. These calls here, and then also these calls here. Now, the question that comes up whenever we perform this kind of an algorithm computation is, how correct is this algorithm? Well, there is a way to prove the correctness of Prim's algorithm. So let's assume that we have G as a connected and undirected graph, the one that you see on this side, and let S be the set of edges that we have for Prim's algorithm. And what we do is we start by selecting an invalid edge. We're going to try to prove by contradiction. So this is why we're picking up an invalid edge. Which one is the invalid edge? It's this one here, is X and Y. And the reason why it's an invalid edge, it's because it forms a cycle. And by definition, we know that we should never form a cycle. Then we can let V prime be the vertices that they're incident to S, and T be the minimum spanning tree that contains all of the edges, but not X and Y. So if edge X and Y is not in T, in the graph that we're looking at, there must be a path in T from X to Y, because T is supposed to be a connected graph. And inserting the edge, sure enough, creates a cycle, and there is exactly only one edge on this cycle with one vertex, and we call this VW. And we're talking about this piece here. So, since Prim's selection xy over VW and W VW is greater than the weights of x and y, we could form a new spanning tree for VW, V, and W in T, proving this there's a spanning tree. But WT prime is clearly no greater than the weight of T. But this means that T prime is indeed an MST, yet it contains all the edges on S, which also include X and Y. This is a contradiction. This is a contradiction, and therefore it's not what we should have expected from the algorithm. So by selecting an invalid method, we were able to prove that Prim's algorithm does indeed find the minimum spanning tree. Now, looking at this activity, we realize that we can do it also with edges. In the next lecture, we're going to discuss how we can perform exactly the same computation using Kruskal's algorithm, an edge-based algorithm.